Awesome. Okay, let me share my screen. So, like Doug said, we're going to talk about machine learning based segmentation. And the reason I wanted to just show a couple of other options is because this is a super popular technique right now. And so it's great to use IntelliSys and Zen if you have access to it, which most of us do now. But for example, I'm working on a Mac, so I'm not able to use Zen regardless of whether the license is publicly available. All of you, of course, have access when the facility is open or via remote access to any of the workstations because those have a license for Zen. But let's say you want to be able to do it on your home computer, or you already are using, let's say, Fiji or some other software, and you want to implement some open source solution for machine learning based segmentation. I just want to give a couple of examples of other options for machine learning based segmentation. And this is much broader than just the couple of examples that I will show you. So of course, machine learning just means any instance where we're not telling the algorithm explicitly how to say separate things into foreground and background. So when you do a threshold-based segmentation, you're saying, okay, in this 8-bit image, anything that's higher than 100, any gray value that's higher than 100 gets called foreground, and anything below 100 gets called background. So that's an explicit separation between foreground and background, whereas machine learning is you might provide some kind of training data or some kind of information that you expect the algorithm to learn from and learn the appropriate separation of your data, in this case, foreground, background, to do an image segmentation. And so the two examples that I'll show today are not necessarily the only examples of this, the only places where you can apply machine learning in your image processing. But hopefully they're helpful to get you started. So the first thing that I wanted to show you is a sort of standalone software called Ilastik. This is software that you can download for free on ilastik.org. And I wanted to show this because it's maybe the most similar to what we saw in Zen's IntelliSys module, because it's sort of a full workflow from beginning to end, from image segmentation to maybe analyzing something about those objects. And so I thought it would be the most helpful comparison. So typically you open this window up and you'll see this option to create a new project. And there's a bunch of different kinds of workflows that you can start in these projects. And I would really encourage you to go on their website, ilastik.org, because for each of these sample projects, they have documentation of a sample workflow, for example. And so it's really easy to get started by looking through those. And I'm just going to highlight a few tips as you get started with this. So I'm first going to actually open one of my own projects that I already have, just because I already loaded the data into it. And in this case, it was just a pixel classification project. And it's using the image that we saw last time when Chris did his demo of IntelliSys. We had this image where, if you didn't tune in last week, basically the problem is that this is a binary image. It just has white and black pixels. But let's say you wanted to segment out these circles here. This is a challenging problem because you couldn't, for example, use a threshold-based segmentation, because all of those bright white pixels, which you might want to call your foreground, are the same gray value as all of these white squares that you might want to call background. And so this is an example where you're not only segmenting based off a single rule, like some single threshold, but you want to take into account the context of a pixel as well. So this is not only a white pixel, but it's also in the context of this sort of mishmash of white and black pixels, whereas this white pixel is in an environment of equally bright pixels. And so you might want to take that into account in order to teach the algorithm some rules on how you might segment this from this background as well as this background, for example. And so that's one of the key parts of implementing machine learning for segmentation, is that we typically, not that you always have to do this, but for image segmentation, what people have found works really nicely is not only taking the information in this image as it is. So for example, this gray value being 255, this gray value being 0, but So taking into account what is the neighborhood, for example, what is the surrounding information of a pixel here versus a pixel here versus a pixel here, and we'll see how you might do that. And then you take all of that information, the information about that native pixel and the information of its neighborhood, and you use that to learn some rules about why these pixels are different from these pixels over here, and that allows the algorithm to separate them. So, okay, how would you actually implement this workflow? So the first thing it asks you to do is just put in some data. So I already loaded in this image here. It doesn't take CZI, so it doesn't have like the bioformats interpreter. So you have to load in TIFFs, for example. But this was a TIFF, so I just loaded it in. And then you have this second tab called feature selection. And this is maybe comparable in parts to in IntelliSys, when you can choose, there's a drop-down menu that says like basic features, and there's different numbers next to basic features, and then deep features, and a number of different out there. And it's basically saying what is the sort of list of information I'm going to give about each individual pixel. So let's see what that looks like. I actually just went through and selected all possibilities. So all these check boxes, I just checked all of them. So what does that mean? Well, first, let's look on the left here where it says there's 3 sort of categories of what these features are. So we have color and intensity. So does the color of the pixel matter, or does the intensity of the pixel matter? And usually it does. Like usually in our images, that's something that we're used to, separating things based off of color or intensity. And just to note, this is of course a black and white image, but if you had, say, a multi-channel image, you would have 2 sort of options here. One is you take each channels as a grayscale image and analyze them separately, or you could take all of your channels and turn it into, say, an RGB image and analyze it as that RGB image. And so then that color would tell you something about what channel was in a given area of the image versus another. And then we have edges and textures. So this might be an example where, edges are, we certainly have a lot of edges in this image. They might be informative, and also texture might be informative. So the fact that this is sort of locally very noisy, lots of white and black pixels mixed together versus any of these sort of straight lines, that might give us some sort of difference on how we would separate this from this background. And there are, subcategories here, but we're going to ignore that for right now. We're just going to say, yep, all of these features might be important, and click OK. And then what you're able to see is now I have this big long list of images. So when you originally just load in data, you would have the raw data. And this is what we are used to thinking about using for image segmentation. So here's my raw data. It's a bunch of gray values arranged in this grid. And I'm going to pick a threshold and say, okay, anything above that value, I'm going to keep. But now these features are how I've gotten extra information about each individual pixel. So for example, let's look at Gaussian smoothing. This was one of the filters in this feature set that was under color and intensity. Okay, so probably a lot of people have seen what Gaussian smoothing does before. So I'm going to go up and up where this sigma value is increasing, and you can see what it's doing to the image. Okay, so now if you imagine taking all of these images here, you'd have, for a given pixel, imagine a pixel right here on the edge of this blob. It would be white in the raw data. But by the time we get to a large sigma Gaussian smoothing, it's now a gray pixel. But it's lighter gray than, say, something that was right in the middle of that circle. And maybe one of these pixels in the white is actually still purely white because it never got influenced by any of these black pixels here. So that's what this Gaussian smoothing is doing, is it's taking a single isolated pixel and having the nearby pixels influence what that gray value now is, such that these circles are all gray because we sort of mixed the white and black that made up those circles. And pixels that are in the middle of a large black region or the middle of a large white region still look black or white, even once you've smoothed them quite intensely as far as this image is concerned. So as we step up with the sigma value basically telling us over what window are we calculating these values, we can see that the image gets more and more blurred, Or we can also think of it as each individual pixel is being influenced more and more by its distant neighbors. So is it being influenced by local neighbors or very distant neighbors? And you have to have a high sigma in order for it to be influenced by very distant neighbors. So that's the key idea to all of these filters, in fact. Even if it's not Gaussian smoothing, if it's, say, something that gets us an edge, so this is an edge filter, we can see that any points where there are edges in our image have a sort of higher signal here, or higher contrast. And as I step up the sigma once again, this is again referring to that Gaussian smoothing that's done prior to taking the edge filter. So as I go up and up and up, I can see that this image changes. And so imagine previously you just had a single pixel that you were considering here, and the only information you had about it was maybe its location, but just the value that it was 255. And that 255 was all you were going to use to separate foreground and background. But now you have the gray values from all these different images, which represent not only that pixel, but also something about the neighboring pixels. And similarly, all these edge filters. And so you can imagine combining all this information to tell you a little bit more about that individual pixel. And you can go through and explore all these different possible filters that you can use and the kinds of information that it brings out in your image. And it allows you to choose which features you want to use to train this segmenter of separating, say, foreground and background. And maybe that's a little bit of information overkill. So in the IntelliSys module, for example, it just says, basic features 25 or something. So it's saying it's going to use some features and it's going to use 25 of them. But you don't have the ability to select at what scales do you want to use certain features, which filters are more appropriate for your image. So if you have an image where you really want to separate based off of edges instead of intensities, then you could use something like Ilastik to really bias the model to pay attention to edges instead of intensities. But you could also say that, well, I'd actually prefer it to just give me some basic feature set because I don't want to go through the trouble of stepping through all of these filters and understanding which is the most useful in segmenting my data. So you also have that option here. You can go into the training tab, and instead of pre-selecting some features that are most relevant to your image, you can actually do a little bit of training, meaning paint what we want versus what we don't want. So these blue lines, this label 2, we could say was background, label 1 was foreground. This is something that we saw last week, how you just sort of paint on the image. And then with that training data, you can have the software suggest features. So you have this button here, suggest features. And so I can say, based on that training data, I want 10 features, or I want 20 features, or however many features you want. And you ask it to select the best features that would best separate the data. And you could do this any number of times to get a long list of different feature sets over here. And you could click through, in which case did the segmentation do the best. You can see at these edges here, there is a slight difference between how well they do. But also down here in this corner, you can see, okay, when I did my user-defined features, which is, I just selected everything, I can see what the computation time was in seconds. And I can see, I can compare that to, okay, I asked it to select 10 features that it thought did the best. And the computation time was about half of what it was here. And so, okay, I saved some time probably because I had far fewer features, but I can also look at the out-of-bag error. So this is something that I mentioned last week when people were wondering, how do you sort of understand how well this is doing? You're training this model to separate foreground from background in this instance. And how do I tell if it's doing a good job? What's a number that I can say, okay, it's doing this well? This out-of-bag error is one example of a number that you could provide to say how poorly or how well the model is doing. But it does require that you put in a decent amount of training data. So here I can see that using these 10 features, although it was faster, it actually did a bit worse than just my original user features, which was just, selecting everything. And so maybe this is a pretty small image. I'm okay with waiting half a second more to get a, halving of my error, for example. And so I might just stick with the user features that I got previously. But you could imagine providing quite a lot of training data and trying a number of different combinations and really being able to defend your choice of features as far as how well they did in separating foreground from background in this instance, or however many classes you have. And so, okay, I'm going to select that feature set. And then you do all the same sorts of things that Chris showed you last week. So you paint on the image to provide more training data. You can have a live update of how well it's doing. You can look at your segmentation, or you can look at the probability maps, which is not just a binary image, but actually shows areas where it's more or less confident as far as whether this truly is label 1 or label 2 or something in between. And then you can export this, you can do some batch processing, all sorts of things. And I'm not going into great detail on this because there's tons of documentation on the website, and this is not maybe a very interesting biological image to go through the details of how we would segment this. But I just wanted to highlight how you can explore the feature sets that you're using that are behind this machine learning algorithm and how it's separating these objects from the background. So to actually show a real biological data set, I'm just going to open up another project. Actually, let me just do this. So here is an example where I'm going to use the pixel classifier plus the object classification. And the motivation here is that I want to highlight that this pixel classification is not finding cells, for example, or finding nuclei or finding RNA spots. All it's doing is semantic segmentation. It's saying for each pixel, do I put it in bin 1 or bin 2 or bin 3 or bin 4? It's not necessarily coalescing those and saying this is an object. And it's definitely not saying this is a cell that's dividing or a cell that's dead or a cell that's CFOS positive or whatever it might be. And so that would be an example of instance segmentation, which is what you can do in this kind of workflow where you start with pixel classification and then you do some object classification, which is more of that instance classification. So again, you start with your input data. I loaded in this more realistic biological data set. So this are some neurons in, I think, a mouse brain. And again, you can start with some feature selection. I already did this. I already provided some training data, again, painting on the image like we did last week. So I, painted some cell bodies. I said, okay, this is all background. And in fact, I was sure to paint over some of these neurites because in this case, in my example, I just want to find cells. I don't care about any of their processes. So I just want to find cell bodies, and they're dimmer, and they also have a slightly different texture than a nice round cell body. And so it's actually fairly straightforward for this to segment those kinds of objects. So I can take a look at how well it did. So if I hit this live update, I want to look at the segmentation. Okay, so this is, I didn't provide it a lot of training data, and I could certainly spend more time training this. I could probably put a few images in here and train them on multiple images. But for now, with just a small amount of training data, it's not doing horribly, so it's finding the cells. It's also finding some other things, probably some bright parts of the processes. But for the most part, it's finding all the cells that I want. I was sure to add some boundaries in here with my background label too. And so it's doing okay. I could spend some more time on this step, but I'm going to go ahead and move on to the next step to show this kind of object classification step. And so, like I said, this is just semantic segmentation. It's just decided for every single pixel, should it be yellow, label 1, or should it be blue, label 2? But it's not necessarily saying that this is a cell and this is a cell and that this is a cell and this is a cell. It's really just saying for each individual pixel, yellow or blue. But then once I want to start finding objects, I can go to this thresholding step. which is basically taking this probability map. So you can see there are some cases where it's quite certain that this is yellow, and it's quite uncertain that some of this is yellow. So we can see that it has a light yellow tinge to it, but it's not quite sure about it. And even some of these dimmer cells, it's maybe not so confident that it should be label 1. And so I can threshold that probability map. And so the probabilities are going to be between 0 and 1. And so if I set my threshold at 0, then I'm going to get nothing or everything. I'm not going to get any objects because everything will pass the threshold. And if I set this maybe too high, then I'm going to get some objects. So now it's starting to combine these pixels to say that they're objects. So it's saying if it passes a threshold, and then if all these pixels are touching one another, then I'm going to call that an object. And so you can see we've added a number of other colors to indicate that these are a bunch of separate objects. But I've probably set the threshold too high because it's missing a bunch of these cells that I successfully found with my pixel classifier, and it's not really finding the whole object. You can see that this is like shrunken relative to the entire cell. So I could go back to the pixel classifier and make it more confident on each of these pixel predictions, and then keep the threshold this high, or I could simply lower the threshold to something like this, and then see, okay, that's finding basically all of the objects that I want, all of these cells that I want, it's finding them as objects, and it's not combining some of these. So, you know, I purposefully drew some of those boundaries in my pixel classifier. Another thing that you could do is, let's say you didn't train the pixel classifier to recognize boundaries, you could, in this thresholding step, try and find some boundaries between different objects. And you would use, I was using this simple threshold method, which is just setting a given threshold, maybe with some smoothing in the X and Y dimensions. Or I could do a more complex method where I basically set 2 thresholds, and the first threshold finds like the seeds of all the objects. So it might find the center of each of these cells. And then the final threshold would allow that seed to grow out and fill the rest of the object. And so you could imagine that if you had 2 nearby cells, maybe the center of those cells is where it's most confident that it's found a positive pixel. And so it would set the seeds there, but you would still have, say, 2 seeds, one here and one here, and then it would still allow them to grow out with that second threshold to find the entirety of the cell body. But in the case of this image, the simple threshold works fine. But again, 2 different strategies, either focusing on the pixel classifier and training it as well as possible, or working on this thresholding step. And this, the parallel to this in IntelliSys is maybe in that analysis workflow, where you do things like filling holes in your objects or setting some size thresholds in your objects. That might be the sort of parallel to what I'm doing in this thresholding tab here. And then we want to start classifying these objects, because right now I've found objects, but what if I wanted to say something about cell shape or cell size or cell intensity to classify them as particular instances? So for example, I don't actually know what this is an image of, but let's say these cells are expressing CFOS. Probably not, because there's so much fluorescence in the processes, but let's just say it's CFOS. And you could classify these as CFOS positive or negative cells. So for those who've never worked with CFOS, just bright cells or dim cells, for example. And so I might go into this object feature selection, and this is now selecting features not like we did before. So remember, we did feature selection before, where we were basically filtering the image. We were doing that Gaussian blurring, or we were using an edge filter. Here, we're gonna basically take much of measurements of the objects. And it even encourages you to compute more features at once, to just sort of compute as many as possible in this step, because it's not very computationally intensive to just compute them all at once. But to do many, many rounds of that takes more time. And so you could select as many features as you want. So you could say, I want all the standard object features, and I want all the convex hull features because I'm interested in these sort of blob-like cells. I'm not going to do the skeleton features. Maybe if you were tracing membranes or processes, that would be more useful. And you can also choose some of these features are the, say, the mean intensity or the mean intensity in the neighborhood of the object. And you can change what sort of, where is the neighborhood? How large of a window outside of my object do I want to consider? And you can calculate all of those. And then you can start doing object classification. And so in this case, instead of painting on my image, it looks a little bit different. So let's get rid of the binary image. I'm just going to look at the raw input. But these are the objects that I've segmented, and you can even see them in their different colors if you want to. So those are all my objects. But now I want to separate them into two classes, positive cells and negative cells, okay? And so I'm gonna paint some positive cells, but all I'm doing here is I'm actually just clicking once, and it's gonna say, okay, that object is a positive object. And maybe I think this one is also a positive object. And then for negative, maybe I think this is a negative object. This is a negative object. And then I want to live update. And what it's doing is it's training an object classifier rather than a pixel classifier. So none of these background pixels that were not classified as objects to start with, they're not considered here. It's just taking each of these instances of an object and classifying it into a pool of positive and negative cells. And you could, of course, come up with more classes here, just like in the foreground, background pixel classifier, I could have gotten more complex and done, say, cell body, neurites, and background, for example. And then you can export this information. So if you configure what you want this table to be, you can choose what features. Now these are measurements, right? I want for each of those objects, I want to measure its mean intensity, and I want to export that. Any sorts of, shape features, you can export all of this information. You can then load it up for some batch processing. So all these rules that you just set for both pixel classification and object classification, you can batch process, say, a whole folder of images, or you can do this blockwise object classification. And the idea of this is that you saw this was pretty fast for this tiny image, but let's say you have a very large tiled image or maybe a Z-stack. That can be pretty RAM intensive to do this classification over those really large images. And so it gives you the option to process these in blocks. And you have two parameters, the block size and the halo size. Think of this as like the tile size, like what's the size of the image that you want to process in one iteration. And then the halo is like the overlap between those tiles. So imagine you have an object that's sitting on the edge of a tile. You might not want to miss it because it's sitting at the edge of one of your blocks. And so the halo is like that amount of overlap where it would process a 512 by 512 image plus 64 pixels on any side. And then it would move over to the next 512 by 512 block, but still sort of extend itself by 64 pixels or however many you put here. So this is a way where you can train both the pixel classifier and the object classifier, and in a nice sort of clicky interface, do a lot of batch processing. So no scripting necessary, but still really possible to do easy like batch processing, even if you have really large images. I will say that if you are interested in scripting any part of this, there are ways. This is, I think, all Python based. So you can add in, say, your own features. If there's a feature, a filter set that you want to use as a feature for pixel classification or object classification, you can add that in yourself by writing a Python script, and there's good developer tools on the Ilastik website. So if there is something missing, it is open source and you can add things to it, but there is no scripting required in order to do all of this batch processing. Just as one quick alternative, I wanted to show the options in Fiji. Because I know in the past couple of weeks we talked a lot about Fiji, and so if you have a workflow that you really like, there are a couple of options to do machine learning based segmentation in Fiji. One that I showed a couple of weeks ago just very briefly is the Weka segmentation. So if you go here under plugins, segmentation, the trainable Weka segmentation window. This is a really nice option. Again, all the same ideas. I'm gonna, paint on the image, add it to class 1, paint on the image, add it to class 2. You can save a class. So I would then need to train my classifier. I could save it. I could apply it to other images that I didn't have any training data on. So all the same concepts here. But for batch processing, really your main option is scripting the batch processing, which is possible. There's lots of great guides on the Weka documentation site, on the ImageJ website, but just be aware that batch processing is maybe not so easy as just doing it in Ilastik. But one advantage here is if I go into settings, not only can I select what training features I want to include in this pixel classifier, but I can also choose what classifier I want to use. So in Ilastik and in IntelliSys, you're using a random forest as your classifier. But there are other kinds of classifiers you can use. And in fact, someone asked about this last week. So Weka is not a Fiji thing. It is a sort of machine learning toolbox that is much broader than just Fiji and just image processing. And so you can choose any number of classifiers. If you know what all of these are and want to try 100 of them out as you're doing your image processing, by all means, you can certainly give that a try. I think there's a consensus that random forests work quite well for segmentation of biological images, but you might want to show that another classifier maybe doesn't work as well, or maybe takes a lot longer, or whatever metric you want to choose to show that it's the best. But those options exist. And one case where using a different classifier might be interesting is in the case of color-based segmentation. So for this image, and again, someone asked about this last week. Someone asked about k-means clustering versus this random forest versus other classifiers. And in this image, you could imagine a scenario where I paint, this part is green and this part is sort of whitish, but this background is really white, and then this ruler is sort of brown. And I could paint on this image to train some pixel classifier to segment it in that way. But I could also maybe just rely on the fact that there is rich color information in this image and see if maybe some other kind of unsupervised classifier would allow me to segment this image. And so another option here, instead of this trainable segmentation, is to use this color clustering. So if I click on that, it's going to give me options for, what kind of color space do I want to segment this image off of? What percentage of pixels do I want to use? And then I can also choose what cluster I want. So I'm going to use simple k-means in this case. And if I just hit run, it's going to give me two classes. It's going to start with k equals 2, so that I get like a foreground background separation. But I can also come in here and say, I want 5 clusters instead. Of course, there's a lot of other information here that you can change, but I'm just showing you one example. Changing the number of clusters to 5, and then hitting run. And now I'm segmenting the ruler, I'm segmenting the 2 different parts of the leaf, I'm segmenting the background into these 5 different clusters, 5 different classes. You can look at the data. So if I want to look at how these different parameters sort of how they led to separation into these 5 classes, I can look at the raw data itself, and this might be something interesting that you would want to show alongside some publication result. So that's an example of choosing a totally different clustering algorithm to segment your image that requires no training data at all. So it's an unsupervised method. It's slightly supervised because you're providing the number of clusters, but you're not providing that training data to segment the image. And so Weka is really nice for that reason, because it hasn't sort of predetermined what clustering you want to use. It provides you probably overkill, too many options for classifiers. And so you can go with the tried and true, or if you have some interesting different data, maybe the tried and true doesn't actually work so well. And so you have all the options in the world to choose a classifier that's appropriate. And like I said, the only downside is if you're not yet comfortable in scripting in Fiji, that really is the best way to automate some of these and do batch processing. But thankfully, there's a lot of existing scripts online that can get you up and running. And of course, that's what we're here to help with. So if any of these options look interesting and you are having trouble getting started with one image, or you're having trouble changing it into a batch processing mode, just let us know. We're happy to Zoom with you directly. You can ask questions in these office hours, or you can even do a screen recording and send that to you, whatever is easiest. But these are two examples of like open source solutions to machine learning based classification, but they are certainly not the only ones. So maybe there are others who have had success with other types of machine learning based segmentation, but both of these should be compatible, I think, on any platform. And they don't require any licenses. So if anyone has questions, I can answer them. I can maybe go through different parts of the software if they're interesting. But that's all I had to say.
Thank you, Erin. That was good. I actually haven't looked at Ilastik in a long time. It's come a long way.
Yeah, they have a lot more options now. And that object classification, oh, that's one thing I should say, is that Weka segmentation is just the pixel classifier part. So it didn't have the object classification, but you could implement that through other features in Fiji, for sure.
Question. We had it last time, the possibility to have additional classes like the borders, and the other question was the nested things like green dots inside the cells.
Yeah, so a couple of things. So the first is that where we were doing the cells versus borders, that's something you would implement in the pixel classifier. So I had two classes. I had blue and yellow, but you could add as many classes as you want. So you could have cell body or nucleus, let's say the border of the nucleus, and then background, for example. As for dots inside of larger dots, that's something that you could use the object classifier for. So imagine you segment all the RNA spots. So you're doing single molecule fish, and you have all of these spots. And you segment all of them, but then you care about the green dots that are inside of the nucleus. And so you would have to do it in an RGB image so that you had that context, but you could classify green dots that are in a neighborhood of blue versus green dots that are not in a neighborhood of blue. And that would be how you could separate based on sort of an object classification scheme, whether it was a nucleus green dot or a background green dot or cell body green dot. That's, I think, the way that you do it in Ilastik. In the Weka segmentation, that is just the pixel classification. So I suppose you could, if you had an RGB image, it is possible that you could train the pixel classifier to pick up on that, but it would be something that.
So a pixel can only be one thing at the time. It cannot be both.
So a pixel can only be one thing at a time, yeah, in a pixel classifier. But you could, like in Zen, that's what you're doing, is you're training a pixel classifier.
Yeah.
Exactly. So you could implement that. Let's say in Fiji, you could implement that, but you'd have to do the layering on your own. There's no maybe there is a workflow, a plugin for it, but not within the Weka segmentation.
Okay, so you would train it like this, and then that, and then that, and then superimpose it later on.
Yeah, but for what I would say is the easier workflow is in Ilastik, training the pixel classifier to find everything, and then use the object classifier to decide, is it in the nucleus or not in the nucleus?
All right.
So you have like two pools of green dots, basically.
Thanks.